Welcome to this explainer. Today, we're putting on our financial detective hats. We're going to learn exactly how to uncover the true story hiding behind investment data. You see, numbers on a page, they rarely tell you the whole truth at first glance. We really need to interrogate those numbers to figure out what an asset is actually doing, how it behaves, and, most importantly, what hidden risks it's carrying.
Now, you might be wondering, how do you actually measure the true risk of an investment? Well, I'll tell you right now. If you're just looking at a simple average return of a stock or a portfolio, you're basically being lied to. Or, at the very least, you aren't getting the full picture. A simple average completely papers over the wild swings, the terrifying drops, and the true risk of an investment. To truly understand an asset, we have to look so much deeper than a single surface-level number.
So here is our investigative map for today. First, finding the center. Second, mapping the distribution. Third, measuring the spread. Fourth, sizing up downside risk. Fifth, looking at the shape of risk. And finally, finding hidden relationships.
All right, let's jump right into part one, finding the center. Okay, the very first step in our investigation is locating exactly where our data is anchored. We need to find the central tendency of our returns. Now, most analysts start with the arithmetic mean, which is just what we commonly call the average. It gives us a representative expected return based on the sample, but there's a massive catch here. The mean is highly sensitive to extreme outliers. A single massive gain or a catastrophic loss can pull that average wildly off base, and that is exactly where the median comes in. The median is simply the exact middle value when you line up all your data. Because it literally just looks at the middle, it remains completely unbothered by those crazy extreme values out at the edges.
And we've also got a third measure for the center, the mode. This is simply the most frequently occurring value in our data set. A set of returns might have one mode, it could have two modes, making it bimodal, or no mode at all if every single return is unique. Yes, these measures anchor us perfectly, but, and this is a big but, knowing the center of our data doesn't tell us a single thing about how far the rest of the data scatters away from that center.
Which brings us to part two, mapping the distribution.
To start mapping out where all those other numbers live around our center point, we chop our data up into buckets called quantiles. Think of these as dividing lines that split our distribution into smaller, much more manageable sizes. We can use quartiles to divide the data into quarters, deciles for tenths, or percentiles for hundredths. Investment analysts use these constantly to rank performance. For example, comparing small cap companies to large ones by sorting them into deciles, or checking if a mutual fund's performance falls into the top quartile of its peer group.
And this brilliantly illustrates how we visualize those quartiles. It's called a box-and-whisker plot. Notice that shaded box right in the middle? That captures the middle 50% of all our data, which we call the inner quartile range. It basically shows us where the bulk of our normal returns live. Then we have those whiskers reaching out from the top and bottom of the box, extending all the way out to the edges of our normal data, which are bounded by what we call fences.
Now, anything that happens past those fences, those are considered outliers, truly extreme returns. But while mapping the data visually like this is incredibly helpful for spotting those wild outliers, a picture doesn't give us a hard mathematical number for our total spread.
So, let's get into part three, measuring the spread.
To get that hard mathematical number and calculate the exact variability, or the absolute dispersion of our returns, we use a few building blocks. The range is just the maximum value minus the minimum, but it really only uses two pieces of information. Mean absolute deviation uses all the observations by averaging the absolute distances from the mean. Variance takes it a step further and squares those deviations, but that leaves us with squared percentages, which are honestly really hard to interpret. That leads us to the absolute gold standard, sample standard deviation. We just take the square root of the variance, which brilliantly expresses our risk in the exact same percentage units as the return itself.
But wait, what if you want to compare two totally different investments, say a super low-risk bond and a high-growth tech stock? Enter the coefficient of variation, or CV. It measures relative dispersion by dividing the standard deviation by the mean. Essentially, it tells you the exact amount of risk you're taking per unit of reward. Because it's a scale-free measure, it allows us to compare completely different investments side by side to see which one actually gives you the best bang for your buck.
Moving right along to part four, sizing up downside risk.
Yes, standard deviation is incredibly useful, absolutely crucial in fact, but it has a major blind spot. It treats upside surprises and downside drops as the exact same thing, risk. But let's be honest here.
Most investors do not care if a return is volatile on the upside. No one complains about randomly making an extra 10%. They just want to know the danger of falling below a minimum acceptable target. They care about the shortfall risk.
To measure that specific danger, we use target semideviation. Instead of looking at all the data, this metric zeroes in strictly on the downside. We set a target, say a minimum acceptable return of 4%. Then, we only calculate the squared deviations for the months where our return actually fell below that 4% target. It completely ignores the upside volatility and gives us a pure, focused measure of downside risk.
Next up, Part 5, the shape of risk.
You see, even downside deviation assumes that our data follows a predictable shape. But as financial detectives, we know the market is rarely perfectly symmetrical. We have to look at the actual shape of our distribution. First, we look at skewness, which measures left or right asymmetry. If returns lean heavily positive or negative, the distribution is skewed. Then we have kurtosis. Kurtosis measures the combined weight of the tails of our distribution relative to the center. It tells us the proportion of our total probability that lives way out at the extreme edges.
So the absolutely crucial point here is understanding the difference between thin tails and fat tails. A platykurtic distribution has thin tails, meaning extreme events are pretty rare. But a leptokurtic distribution has fat tails. Grounding this in reality, if an asset has a leptokurtic distribution, it means there is a much, much higher likelihood of severe, extreme deviations from the mean. In plain English, fat tails mean a higher probability of massive, terrifying market crashes.
Finally, Part 6, Finding Hidden Relationships.
Now for our final step. We know the center, the spread, and the shape of a single asset. But investments don't exist in a vacuum, right? We need to interrogate how multiple variables act together. We measure this association using the correlation coefficient. It's a normalized measure that tells us if two variables tend to move together in the same direction, which is positive correlation, or in opposite directions, which is negative correlation. It's a vital statistic, but warning, relying solely on this summary number is a massive trap.
Now, what's really interesting is this famous statistical concept called Anscombe's quartet. We have 4 data sets here, Roman numerals I, 2, 3, and 4. If you just look at the summary statistics, the x variables all have the exact same mean of 9. The y variables all have the exact same mean of 7.5. The standard deviations are identical, and the correlation between x and y is exactly 0.82 for all 4 sets. Mathematically, on paper, these 4 data sets look perfectly identical.
But let's see how this builds. Look what happens when we actually plot those exact same data points onto scatter plots. The relationships are completely different. Dataset I is a normal linear relationship. Dataset 2 is a massive curve. Dataset 3 is a perfect line completely ruined by one single outlier. And dataset 4 is basically a straight vertical line, again with one extreme outlier. This proves exactly why plotting your data visually is absolutely mandatory. The summary numbers alone completely hid the truth.
As a financial detective, your job is to never, ever take the average at face value. You must locate the true center, map the spread, size up the downside risk, check the shape of your tails, and always visualize your correlations. So I leave you with this. The next time you're handed a pristine report on an asset's expected return, are you going to read the whole story, or are you just going to blindly trust the summary statistics?